Okay. Uh, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. So today our continued knowledge sharing will be talks about the petrophysical uncertainty, and welcome to my reservoir lab channels. Evaluating petrophysical uncertainty refer to the process of assessing and quantifying the potential error or uncertainties associated with the petrophysical measurement and interpretation in oil and gas industry. Uh, this kind of evaluation helps in understanding the reliability and accuracy of the data obtained from the well log and other petrophysical measurements, which are crucial for making informed decisions in reservoir characterization and hydrocarbon exploration. The quantifying of uncertainty in the petrophysical variables such as porosity, water saturation, net to gross ratio in well, it is impact on estimating the in-place volume. It's highlight the importance of considering the interdependent of petrophysical variables, systematic errors, the combined effect of reservoir properties, logging tool response function, evaluation model choice. This kind of sharing also introduce of the concept hydrocarbon port fraction, HGPV, and provide methods estimating the linking uncertainties in each hydrocarbon pore volume with water saturation mapping function. So what is the uncertainty for? This kind of statement, the purpose of significant of uncertainty in the context of reservoir modeling, uncertainty plays a crucial role in assessing properties like porosity, saturation, permeability of reservoir, as well as in making decisions related to the completion and flow. This talk primarily focus on understanding and managing uncertainty in these properties for reservoir modeling purposes. And also we will focus on discussing the uncertainty associated with the properties as they determine and utilized in the reservoir models. The talk aims to address the importance of understanding, managing uncertainty kind of properties for accurate reservoir modeling and decision-making process. This sharing will take chance focusing on quantifying uncertainty in terms of petrophysical variables such as porosity, water saturation, net to gross ratio as estimated well, at impact in place volume estimate. Value properly account for the petrophysical uncertainty can lead to misleading estimate, of course. Number of papers I use material compilation, the interdependent of petrophysical variables, the need to consider the hydrocarbon fraction as combined variable, the significance of systematic errors, the challenge posed by reservoir properties, logging tool limitation, evaluation model choice in estimating the uncertainty. And uncertainty at the well zone levels refer to the level of uncertainty associated with the petrophysical variables within a specific zone of the well. This uncertainty arises from systematic errors, its input measurement, the data analysis method, subject judgment of petrophysics. Estimating this uncertainty requires considering factors such as random error, variation in reservoir properties, and the choice of probability distribution. While these statistical concepts like P10, P90 are used as conceptual guideline for specifying uncertainty. Moving from the well zone to the field level refers to the process of extending the assessment of uncertainty in petrophysical properties beyond the individual well zone to the entire oil and gas level. This step involves evaluating the correlation between errors and uncertainty in different well zones within the field. Assessing this correlation is crucial in accurately estimating the overall uncertainty in hydrocarbon per volume, HCPV, is typically done based on the petrophysic judgment and understanding of the most significant source of uncertainty. Petrophysical uncertainty refer to the lack of precise knowledge or predictability in petrophysical properties, which are properties related to the physical characteristics of rock and fluid in the subsurface. However, it is important to note that this uncertainty cannot be determined by simply varying cutoff values or by analyzing the distribution on specific properties. This method do not provide an accurate assessment of petrophysical uncertainty. Just drawback reference of petrophysical cutoff where it's commonly used to exclude non-producing pay in the reservoir models. The benefit of applying cutoff that they have maintained the relationship between petrophysical parameters at the upscale model grid scale, preventing bias in porosity, permeability, and water saturation distribution. However, applying cutoff can also have drawback, potentially reducing volumetric reservoir connectivity and impacting the dynamic of the reservoir. Traditional cutoff based uncertainty analysis, specifically focusing on the net aspect involved using different cutoff values such as 10, 50, 90 percentile, to estimate performance intervals and quantifying uncertainty in the net pay or net sand. This approach is based on the probability of flow and provide consistent set of results for assessment across a field or basin. However, it doesn't address uncertainty in underlying data or interpretation, limiting its scope. It should be noted that this method only addresses uncertainty related to net pay, net sand, or doesn't consider the underlying the data or interpretation. In the context of uncertainty in petrophysics, again, it is known that petrophysics often prefer to use the mode of probability distribution function as an input parameter value rather than expectation or P50 value. This preference should be considered when specifying the probability distribution in Monte Carlo simulation with best case value placed at the mode and allowing for the skew distribution as needed. Additionally, it is important to ensure that specified distribution respect any physical limitation such as not to gross thickness, net to gross reservoir thickness ratio, and volume of shale staying within range of the 0 to 1. In the concept of net uncertainty and its sensitivity to the cutoff, it's highlight this question related to the net reservoir characteristics are often influenced more by stratigraphy than petrophysics. Additionally, it's mentioned that while most high porosity reservoir, especially for example deep water, are not significantly affected by cutoff, some reservoir exhibit high sensitivity to the cutoff values. Net uncertainty refer to the uncertainty associated with determining the net volume of hydrocarbon in reservoir. In this context, the text suggests considering whether it is more appropriate to use a stratigraphic analog or cutoff analysis to handle this uncertainty. It's also advised tailoring the approach based on specific problem. avoiding simultaneous use of cut-off analysis for reservoir modeling, property uncertainty description, treating cut-off uncertainty independently from porosity and saturation log when assessing the net to gross ratio. Property uncertainty tries to cover and look at the perspective from various sources of uncertainty in characterization and measurement of the geological properties in the context of oil and gas exploration. This kind of uncertainty can arise from factors such as lack of detailed knowledge about the subsurface away from the wellbore, limitation in measurement precision, statistical uncertainty, potential errors in calibration, the accuracy of interpretation due to incorrect model parameters or any assumption. And understanding and managing this uncertainty, we believe very crucial for making informed decision in exploration production of hydrocarbon resources. So, in the wireline logging spectrum analysis, precision refers to the measurement error or statistical variability, indicating how consistent the measurement are when repeated. On the other hand, accuracy of logging refers to the calibration of the tool or the presence of systematic bias, indicating how close the measurement are to the true value. It's possible to have accuracy without precision or measurement consistently biased, but not necessary to close to the true value. And precision without accuracy, measurement consistently close to each other, but not necessarily close to the true value. Precision and accuracy are two important aspects of the measurement. Precision refers to the consistency and repeatability of measurement, while the accuracy, how close the measured values are to the expected value. In this context, from the slide, we can see illustrate the precision, accuracy in measurement. Another picture show example of measurement with uncertainty, including the noise and systematic errors. Another illustration that explains the concept of accuracy in measurement. Accuracy refers to the degree closeness between measured values and true values, while precision refers to the consistency and reproducibility of repeated measurement. Accuracy represents systematic error, which is consistent deviation from the true value, while precision represents random error, which is variability in repeated measurement. In certain state of analysis, it's worthwhile to have an understanding the difference between precision and accuracy. Precision refers to the consistency, reproducibility of measurement, while accuracy, how close the measurement are to the true value. While the precision is important, achieving accuracy with single measurement is unlikely. However, in most applications, multiplication measurement are taken. The focus is on accuracy of the average value rather than precision of individual measurement. The statement precision cannot completely disregard. We believe emphasize on the importance of considering measurement precision when estimating average petrophysical variables. In cases where the number of measurement is low or measurement precision is poor, the uncertainty associated with precision shouldn't be neglected, as it can introduce systematic error in estimation of the petrophysical properties. When we realize a lack of knowledge about subsurface condition between wells in oil or gas field means we are dealing with the geologic uncertainty. It's raises question about the representative of available data and the presence of the factor like compaction trend. For example, understanding quantifying this uncertainty requires kind of collaboration among various aspects. Mappers, petrophysics, stratigraphers, the level of uncertainty, it can vary early appraisal state often having higher uncertainty, while some reservoir with minimal rock variation, such as certainty turbidite, the uncertainty may be relatively small. The distribution of good average provide insight into the variability of the data across the reservoir. Now we talk statistical tool uncertainty in terms of repeatability, where this measurement error associated with the specific tool in the data collection. In the case of from the log, we can from the slides display composite wire. The value 1.65 to 2.65 represent the range of uncertainty for this measurement. Okay, service company aims to minimize this type of error as it can introduce artificial variation in the reservoir by it doesn't impact to overall average values of the well or the field. Combined effect of reservoir properties, different in logging tool response function, choice of evaluation model parameter contribute significantly to the uncertainty in reservoir with heterogeneity. Estimating uncertainty at the log depth increment level should lie based on the error propagation or Monte Carlo method using log, core, evaluation model, and all of those parameter uncertainty is inadequate. So more comprehensive approach is needed to account this source of uncertainty in reservoir evaluation. In the context of measurement, again, accuracy, how close measured value is to the true value, precision, consistency, and repeatability of measurement. When it's happen random error, fluctuation or noise in measurement, which can be reduced by averaging repeated measurement. On the other hand, systematic error cause of consistency between measured and true values. Repeated measurement convert toward the systematic error affecting the measurement accuracy. Interpretation uncertainty, referring to the level of uncertainty in determining the characteristic of the field, such as distribution of net sand in well, for example. It's explained for the field, it's expected 25% of well will have the lowest net sand P10, 50% will have the median net sand P50, and 25% will have the highest net sand P90. Then Monte Carlo simulation were conducted, introduced to analyze the effect of statistical uncertainty, revealing that the difference in total net pay between P10, P90 realization varied 20% for the 10 well field, 2% for the maybe more than 500 field. One of the error in measurement instrument is caused by tool bias, such as calibration or other factors that can introduce systematic deviation in the property being measured. This bias can vary from well to well, leading to the artificial heterogeneity in the reservoir, while the tool bias result in uncertainty and noise in the property measurement. It may not necessarily affect the average value of the property. So next, interpretation uncertainty. This stage with the lack of uncertainty or confidence in the interpretation of the data or result. Systematic bias in the context of refer the consistent error, where deviation caused by incorrect assumption, input, or model use the interpretation process. This bias can impact the accuracy of the well data, ultimately lead to the incorrect field average properties, highlighting the importance of capturing, addressing this uncertainty in order to make a reliable conclusion. As a consequence of making incorrect assumption, using inaccurate input, or employing an inappropriate model, So all of these errors can lead to systematic bias in every well, resulting the inaccurate field effort property calculation. It emphasized the important recognizing, accounting for this uncertainty to ensure accurate assessment and decision making. Here are Herein some example interpretation bias when scenario three different companies are evaluating same zone into wells within I think that deep water Gulf of Mexico discovery. The context specify no equity or political issue that could influence the result. Of course, the data quality is high, including magnetic resonance log scoring through the entire reservoir interval in both wells. The term highlight the potential subjective bias, preconceived nation to influence the interpretation of the data, subsequent conclusion drawn by the companies involved. The reserve uncertainty resulting from evaluation process it alone. In this case, for example, well number one, reserve uncertainty estimated to be 7.5%, while the second well it's much higher, estimated about 7.8%. And this percentage indicate the level of uncertainty associated with the estimate reserve of respective well based on the evaluation conducted. As we can see from this slide, where petrophysical uncertainty become important when it has significant impact of the estimation hydrocarbon pore volume, the crucial consider petrophysical uncertainty when it affect the accuracy of hydrocarbon pore volume estimation in the complex cases with multiple well zone, varying reservoir properties, assessing the degree correlation between errors, uncertainty in different zone is the key step, quantifying petrophysical uncertainty and its impact on the HCPV estimation. Geologic uncertainty, inherent variability, lack of knowledge about the subsurface properties of reservoir, interpretation uncertainty, on the other hand, arise from the subjective interpretation of the data can be influenced by bias. Determining which is more important, it depends on specific context of reservoir characteristic, but some cases, interpretation uncertainty can be larger than geologic uncertainty, especially in reservoir with high sensitivity to the petrophysical parameters. Geologic versus interpretation uncertainty in the context of porosity, permeability refer to the comparison between uncertainty arising geological factors that arising from the interpretation method. The multiple penetration used to assess this uncertainty, calculating low, mid, and high case petrophysics, different infield wide average can determine the interpretation uncertainty. While the range between 10 to the 90 percentile of the mid-case porosity distribution provide the geologic uncertainty. One of the benefits using permeability cutoff compared to the previous indicators derived from the A composite log that permeability is directly related to dynamic properties of reservoir. However, determining the permeability, I think, requires modeling, such as through neural network, as it cannot directly derive from the A logs. This approach allow for more accurate representation of the reservoir behavior and also can improve the reliability of the cutoff selection process. Geologic versus interpretation refer the comparison between uncertainty in the estimation of permeability reservoir. In the context, interpreted uncertainty is higher than geologic uncertainty because of fewer constraint and redundant data availability for estimating permeability. And this implies that accuracy, reliability of permeability estimation are more uncertain due to limited information and constraint in the interpretation process. In another case, for example, another, I think this is another Gulf Mexico field, the methodology involves utilizing all available data to restrict the input for porosity and saturation calculation. Additionally, a probability tree is employed to determine specific low, mid, and high cases used in the evaluation process. And this approach allows for comprehensive analysis of porosity saturation characteristic, considering the scenarios and uncertainty. The different petrophysical scenarios were created for the reservoir model by varying input parameters such as porosity, saturation, permeability at low, mid, and high level. This scenario then constrained and validated using multiple data types such as core samples, well logs, and analog to reduce uncertainty. It is important to note that variation in porosity, saturation, permeability are not simply deviation from most likely case, but rather discrete and repeatable cases used to assess the range of possible outcome. Again, look back with well-test data to revise the range. Another methodology used by, I think, Chevron in the Gulf of Mexico field project, where it's involved analyzing the data obtained from well test, making adjustment or revision the predicted range of values for parameters such as permeability. And this iterative process help refine the model used in the project and improve the accuracy of prediction. The importance of ensuring wide enough range of data in the contact water chemistry analysis, for example, it's highlight that different data source can lead to significant difference in the range uncertainty, can cause a major shift in the estimated values, and also emphasize the need to avoid in the aquifer represent the water phase in the oil lag, as it is common flow assumption. Now we talk about the Monte Carlo uncertainty in geolog, referring the utilization Monte Carlo simulation techniques to represent the present uncertainty related to the petrophysical properties in a consistent and logical manner. This kind of approach allow for the assessment of standard parameter type uncertainty, but it doesn't account for reduction of uncertainty through corroboration. It's also mentioned that the representation of full uncertainty distribution and uncertainty distribution for the zonal average. The process linking uncertainty in the well data and map saturation data, it's explained that uncertainty estimate in well zone average data are obtained using the Monte Carlo based method, while the uncertainty estimate in saturation mapping at the map level are segmented based on representative well areas. These segmentations allows for calculation of volumetric and estimation of average saturation, considering the effect of change in saturation parameters and the uncertainty in the saturation model. The concept of dependence of variables, relationship between different variables, their impact on each other. It is important to distinguish between the dependency of variable itself and dependency of the uncertainty associated with the variable. For example, water saturation, the uncertainty in saturation can be influenced by factors like RWs, cementation factor, saturation exponent, and porosity. However, just because water saturation is related to the porosity doesn't mean that uncertainty arising from using wrong value for M is also related to the porosity. So this process of quantifying uncertainty in calculating water saturation using electrical resistivity measurement, where kind of error analysis in SW, for example, error resistivity base are referring to. This analysis involve evaluating the accuracy, precision of various input variables such as logging data, resistivity device, determining the error distribution. By employing analytical numerical methods, the minimum uncertainty of this variable can be determined to improve the accuracy of water saturation calculation. Dependency of variable refers again relationship between different factors in model or analysis. So in the plot, shown doesn't indicate that uncertainty is dependent. However, when working in hydrocarbon concentration per volume space, combining with high porosity, low SW cases can lead to significantly higher estimate hydrocarbon per volume. In this situation, with varying porosity and SW estimate, it's recommended to combine high SW, low porosity only if most of the uncertainty is dependent. Otherwise, treat them independently in the model. Concept of dependency between variable in reservoir modeling, specifically focus on saturation, permeability, porosity. It suggests that if these variables are related, they should be treated as independent when modeling in reservoir. However, caution is advised when using low, mid, and high estimate of this variable as dependent, as it may lead to overestimation of petrophysical uncertainty. To accurately account for dependency, a holistic evaluation, low, mid, high cases, or the use of Monte Carlo simulation for the three variable is highly recommended. The question posed whether petrophysical uncertainty is consistent across the different well. If the uncertainty is primarily influenced by variations in the model interpretation parameters, then it is not independent from well to well. In such cases, P10 porosity values is utilized in each well to establish a P10 scenario for the entire field, ensuring a consistent approach to address the uncertainty. Again, dependence of variables refer to the consideration high confidence per volume, high hydrocarbon per volume, uncertainty, instead of treating porosity and saturation uncertainty separately. This approach over benefit, especially when comparing data from different scale, measurement technique. However, there are also challenges in applying this method. A discussion of variable dependency, specifically permeability in the context of capturing heterogeneity and uncertainty. It's mentioned common to derive low, mid, high values of permeability from the cross plot will help account for variation in permeability. However, it implies these derived value are dependent on each other and act as a multiplier for permeability without considering difference in heterogeneity. It's also suggests that advisable to consider the permeability heterogeneity separately from uncertainty in average permeability. Well, this implies that these two aspects should be treated as distinct source of uncertainty in order to better understand and analyze them in the system. The concept of uncertainty reduction through corroboration in context analyzing parameter and model uncertainty. It highlights that existing technique for modeling uncertainty do not consider the corroboration of interpretation. Additionally, mention the option of standardized method to incorporate uncertainty reduction from other data sources such as log core samples due to challenge related to the scale and sampling different dependency, the lack of clear mathematically, logically sounds of methodology. Um, the use of corroboration answer to reduce uncertainty in the analysis data. Earlier mentioned that Monte Carlo technique are employed to analyze and quantify. The concept HCPV calculated as porosity multiplied by 1 minus saturation introduce a mean to compare result directly to the original oil in place, allow for comparison of data from different scale methodologies such as core porosity. Again, we can assume those value up and get an equivalent hydrocarbon column for that formation, where we can see all of these possible models. Again, we have P90, P50, and P10 case for all different model. In the situation here, we have very low oil in place simply because most of this point in those model didn't pass the cutoff. So that's mean if we have this kind of uncertainty, we actually cannot book anything based on the P90 case. This is why the uncertainty are so important and why model-based uncertainty is particularly important. Using corroboration to reduce uncertainty suggests the method approach involves utilizing corroboration to decrease or minimizing uncertainty. The techniques likely aims to validate or support finding or conclusion by gathering additional evidence or confirming result through the various means. So the context provide doesn't offer further detail about specific application or field in which this corroboration method is employed. When it comes to the core base, then start, for example, in the petrophysics, if laboratory has procedural errors or weaknesses, it can affect all of the data collected, leading to strong correlation between different well zone. However, if error are caused by an individual laboratory engineer having a bad day, the correlation to other well zone will be low. It is important to assess the degree correlation of error caused by core-based parameter based on the representativity of the data and the variability of reservoir properties within the validity range, as the correlation within the validity range is likely to be high. So, but the correlation between validity range will be very depending on the specific case. Drainage imbibition, oil water centrifuge, another technique used in the study of fluid flow, porous material. The method involves subjecting as example to centrifugal force to simulate the process of drainage, removal of fluid from the pore, and imbibition, absorption fluid into the pores. It is valuable tool for investigating the behavior of fluid, reservoir rock, and understanding their fluid characteristic. The use of corroboration to reduce uncertainty in the data analysis, incorporating multiple source of data, core saturation, capillary pressure, magnetic resonance, nuclear data, and evaluation. The uncertainty range can be iteratively refined to align with the indication from the data. Additionally, ranking of the data based on uncertainty and giving more weight to the data with higher uncertainty can further enhance the accuracy of the analysis. So the challenge in estimating permeability, which is a measure of how easily fluid flow through rock. Permeability estimation is difficult to the limited reliable measurement, and what the issue is related to the scale and other geological features. Um, For example, in certain field, the range of permeability multiplier, let's say typically between 0.5 to 2, but it may be wider and low permeability. It suggested using corroboration, varying assumption to validate the chosen range of permeability multiplier. So, in summary, in dealing with the main uncertainty in petrophysics, the main things that need to be considered are related to the interpretation and the geological factors. Monte Carlo technique can be used to estimate the range of uncertainty, hydrocarbon per volume, it is important to avoid narrow input range due to limited data and corroborating data from other sources, which can help the reduce uncertainty. Additionally, focusing on hydrocarbon per volume instead of porosity, saturation separately can prevent overestimation of uncertainty, while handling permeability uncertainty may involve separation heterogeneity uncertainty from the uncertainty in the average of the value. The largest source of the uncertainty in petrophysics are interpretation of uncertainty and the geological uncertainty. Interpretation uncertainty refers to in understanding, analyzing petrophysical data, while the geological uncertainty relate to the uncertainty in the subsurface geological component. This uncertainty can have significant impact on the accuracy of reliability, petrophysical measurement should be carefully considering when assessing the modeling, the hydrocarbon potential. Monte Carlo techniques is very valuable tool, obtaining an initial estimate of the range of uncertainty in the hydrocarbon per volume. And this technique involves running multiple simulation, randomly varied input parameter to capture the potential variability in the result. And also by using this technique, we can get insight into the possible range of uncertainty, which is crucial making informed decision in the field of petrophysics. Make sure that our range of input is not too narrow, narrow out of lack data. Advise again, setting a narrow range of for input parameters when there is insufficient data available. This caution is important because narrow range may not accurately capture the uncertainty associated with the parameters being considered. It is crucial to consider a broader range of input to account for potential uncertainty and avoid underestimating the true variability. Corroboration from other type refer the process during multiple source of data to support validation, particular finding or conclusion in given context suggested that by overlaying different type of data, range of uncertainty can be reduced. This approach strengthens the reliability, accuracy of the analysis by considering multiple perspective and source of information. It is also recommended to focus on hydrocarbon per volume instead of analyzing porosity and saturation separately. However, it may be necessary to separate porosity, saturation for modeling purposes. And by concentrating on hydrocarbon per volume, considering is a combined parameter, the risk of overestimating uncertainty can be minimized. Dealing with uncertainty and permeability suggested it is more effective to separate uncertainty rising from the heterogeneity, variation, permeability within the reservoir from the uncertainty in the average of permeability value. So by doing so, the accuracy of assessment permeability uncertainty can be obtained. This approach allows for better understanding the impact of heterogeneity and permeability helps in mitigating the overestimation of uncertainty. So I think that's all at the moment from my today's sharing. Hope everyone enjoy listening. See you on soon on the next session. Thank you.